The earth trembled once again in one of its most isolated corners, where icy winds tear across a vast, storm-ridden sea. On October 10th, 2025, at precisely 20 hours and 29 minutes Coordinated Universal Time, instruments across the globe registered a massive shock. A magnitude 7.6 earthquake deep beneath the Drake Passage, that unforgiving stretch of ocean separating South America's southern tip from the Antarctic Peninsula. Occurring at a depth of just about 10.5 kilometers, or roughly 6.5 miles, the quake unleashed an immense release of energy along a concealed fault system few had ever thought capable of producing such violence. In a region that rarely stirs, the sudden jolt seemed to come out of nowhere. Just 7 weeks earlier, on August 22, a magnitude 7.5 tremor had struck nearly the same coordinates, 60.319 degrees south and 61.922 degrees west, at a similar shallow depth of 10 kilometers. Before that, the Drake Passage had lain mostly dormant for decades, its last significant quake being a magnitude 6.0 in 2009, and before that, a magnitude 6.1 in 1964. To witness two great quakes in the same season was, to seismologists, almost surreal. What had awakened this long silent fault beneath the icy waves? The October event's mechanism was confirmed to be strike-slip faulting, meaning that the Earth's crust sheared horizontally, side against side, rather than thrusting vertically. The movement was shallow but extensive, consistent with the sudden rupture of a long and narrow fault plane, estimated to stretch around 140 kilometers in length and 20 kilometers in width, roughly 87 by 12 miles. The focal mechanism suggests two possible orientations. One, a left lateral motion on a west-northwest trending fault, and two, a right lateral slip on a nearly north-south fault. Either scenario points to a dramatic horizontal displacement of crustal blocks within the Antarctic plate, just southwest of its contact with the Scotia Plate. It is precisely this detail, that the quake occurred within a tectonic plate rather than at its edge, that has astonished geophysicists. Intraplate earthquakes of this size are exceptionally rare. Most of Earth's major tremors occur at convergent or transform boundaries where plates collide or slide past one another. Yet here, far from the main subduction fronts of the Andes or the great mid-ocean ridges, a violent rearrangement of crust has taken place inside the Antarctic plate itself. Such events hint that ancient buried weaknesses, perhaps remnants of faults dating back tens of millions of years, may still be capable of rupturing when stress redistributes across the plate. The Drake Passage is a geologically chaotic region. Once, in deep geological time, South America and Antarctica were joined. Around 40 million years ago, spreading forces tore them apart, opening the seaway that now allows the Antarctic circumpolar current to circle the globe. The tearing left a patchwork of transform faults, fracture zones and microplates. Among these, the Shackleton Fracture Zone and the boundaries of the small Scotia Plate act as major shear zones linking the Atlantic and Pacific realms. But between them, across the interior of the Antarctic Plate, smaller lineaments run unseen beneath thick sediment and oceanic crust. Many of these have never been mapped, because the Drake Passage lies among the most remote and inhospitable seas on Earth. When the October 10th quake struck, its energy radiated outward across the sea floor, shaking sensors as far as the Antarctic Peninsula and Tierra del Fuego. Though there was little on land to feel it, the seismic waves told their own story. The rupture propagated laterally, tearing through the crust with tremendous velocity. This kind of strike-slip motion typically involves relative motion between blocks of several meters in a matter of seconds. The stress drop, the difference between the pre- and post-quake tension, must have been enormous, enough to release the equivalent of hundreds of atomic bombs in energy. Hours before the main shock, smaller quakes had already been stirring. At 18 hours, 13 minutes, a magnitude 4.9 tremor rippled through the same corridor. Minutes later, a magnitude 5.4 and a magnitude 5.7 followed, each at 10 kilometers depth. They were early warnings, foreshocks hinting that a major fault patch was nearing its breaking point. At 19 hours 9 minutes came another, magnitude 4.8. Then, after the main rupture, at 20 hours 29 minutes, the region convulsed again. A magnitude 4.6 at 20 hours 9 minutes and a magnitude 4.7 at 21 hours 46 minutes. The seismic pattern was unmistakable, an escalating series culminating in a massive release, followed by a cluster of aftershocks spreading outward along the fault. In the hours following, the aftershock field extended roughly 100 kilometers from the epicenter, forming a linear trend across the seabed. That geometry suggested the fault orientation was more likely west-northwest to east-southeast, supporting the idea of left lateral motion. Each aftershock represented a small section of crust adjusting to the enormous change in stress. The main rupture had likely caused displacement of several meters at depth, with smaller cracks rippling through the brittle crust above. For geologists, these patterns are like fingerprints, telling them how the fault moved and where the greatest strain now lies. The mechanics of strike-slip earthquakes are governed by shear stress. Imagine the crust as a deck of cards being pushed from opposite ends. When friction overcomes resistance, the layers slide past each other abruptly. In this case, one side of the Drake Passage fault moved horizontally relative to the other, relieving pressure that had been building silently for perhaps centuries. The earthquake's shallow depth indicates the rupture occurred within the brittle upper crust, where temperatures are low enough for rocks to fracture rather than flow. Below 20 kilometers, rocks behave plastically, absorbing strain without breaking. But near the surface, rigid oceanic crust can suddenly snap, generating seismic waves that travel thousands of kilometers. Particularly intriguing to scientists is how this quake sequence fits within the broader pattern of Antarctic plate motion. The Antarctic plate is slowly moving northward and counterclockwise relative to the smaller Scotia plate, at a rate of only a few centimeters per year. Over time, this steady grind concentrates stress along any misaligned weakness in the crust. If those weaknesses align with the direction of plate motion, they may eventually reactivate as strike-slip faults. Thus, while the main plate boundary might absorb most deformation, some is transferred inward, where hidden faults can awaken without warning. The August and October quakes together may indicate such a process at work. Progressive reactivation of an ancient fracture zone or transform fault. When one segment ruptures, it redistributes stress along adjacent portions, potentially triggering a second failure weeks or months later. This domino effect is well known in plate interiors, though rarely so well documented. What is remarkable in this case is the scale. Both quakes exceeded magnitude 7, implying enormous fault lengths and energy releases. For that to happen, the crust beneath the Drake Passage must be heavily pre-stressed and mechanically strong enough to store elastic energy over long periods. Even in the age of satellites and ocean-bottom seismometers, the Drake Passage remains a frontier. Its seafloor topography is rugged, carved by transform ridges and deep troughs. Bathymetric maps reveal scarps rising hundreds of meters, probably the surface expressions of ancient faulting. Some of these ridges run nearly parallel to the path of the recent earthquake sequence, hinting that the newly ruptured fault could connect to one of these scarps. Others may form secondary shear zones, accommodating motion between small crustal blocks trapped between the Antarctic and Scotia plates. Every quake, then, becomes a probe into the hidden architecture of this undersea world. The waveforms of the October 10 event will allow seismologists to perform what is called finite fault inversion, a reconstruction of how the rupture propagated across the fault surface over time. By studying the arrival times of P waves and S waves recorded across multiple continents, researchers can estimate the direction, velocity and duration of slip. Early models suggest that the rupture travelled primarily to the northwest, consistent with the distribution of aftershocks. The total rupture duration may have been around 20 seconds, a blink in human time, but long enough to shift massive sections of crust sideways by several meters. To understand why the Earth has stirred so violently here, one must look deeper, beneath the thin veneer of rock that floats atop the mantle, where the slow churn of convection drives the relentless drift of tectonic plates. The Antarctic plate is among the largest on Earth, extending from the icy continent outward beneath vast stretches of ocean. Its boundaries are complex. To the north, it rubs against the South American and Scotia plates. To the west, it meets the Pacific plate, and to the east, it brushes against the African and Australian plates. These interactions generate diverse regimes of compression, extension, and shear. The Drake Passage, lying between South America's Cape Horn and the northern tip of the Antarctic Peninsula, is a critical gateway where those stresses converge. The small Scotia plate acts as a mechanical buffer between the larger plates, yet its edges are riddled with transform faults that absorb and transmit strain like the gears of a planetary machine. Over millions of years, this region has seen the birth and death of oceanic crust. The spreading that once opened the Drake Passage left behind crustal scar, ancient fractures now reawakened by shifting stresses. When two adjacent plates move at slightly different angles, a portion of the stress can migrate into the interior of one plate. That internal stress accumulates quietly, unnoticed, until one day a buried weakness, an old suture, a fault sealed by time, reaches its breaking point. What follows is instantaneous. Brittle failure, a sudden rupture, and the release of energy that travels through rock as seismic waves. The October 10 quake is the surface expression of this invisible geodynamic process. Unlike subduction earthquakes, which involve the vertical thrusting of one plate beneath another, strike-slip quakes, such as this one, are characterized by horizontal displacement. The crust effectively tears itself sideways. Because the motion is lateral, it produces distinct shear waves that travel efficiently through the lithosphere, giving scientists valuable information about the fault's geometry. The shallowness of the Drake Passage rupture means the earthquake's slip zone was near the brittle ductile transition, where the crust stops deforming plastically and instead fractures catastrophically. At this level, typically around 10 to 15 kilometers, 6 to 9 miles below the seafloor, temperatures and pressures are ideal for building elastic strain that can be released explosively. The pairing of two nearly identical major earthquakes within 7 weeks suggests something far more intricate than coincidence. One possibility is stress transfer. When a fault ruptures, it does not simply release energy and go silent. it reshapes the regional stress field. Certain sections of adjacent faults become more compressed, loaded, while others are relaxed. Seismic models show that after the August event, the surrounding crust was left with pockets of increased Coulomb stress that coincided strikingly with the location of the October rupture. This implies that the first quake may have primed the second by subtly redistributing strain along a neighbouring fault segment. The Earth, in effect, was setting up its next move. This behaviour resembles what has been observed in other transform systems. In California's San Andreas Fault, for instance, large strike-slip quakes have been known to cascade along segments over months or years, each event loading the next. The same could now be occurring along the hidden fault network beneath the Drake Passage. If true, it would mean that this region, long thought stable, may host a complex web of active shear zones extending for hundreds of kilometres. Some geophysicists now speculate that the Drake Passage represents a transitional corridor between the active boundaries of the Scotia Plate and the broader Antarctic interior, where strain is gradually propagating southward. Geophysical imaging may soon shed light on this. Using satellite-based radar interferometry, scientists can detect minute changes in seafloor elevation following large earthquakes, even under ocean water. These measurements reveal the pattern of deformation across the fault zone, helping to map the rupture plane. In combination with ocean-bottom seismometer data, they can reconstruct how the crust flexed during and after the quake. Already, preliminary readings indicate a distinct northwest-southeast trend in deformation consistent with left lateral motion, supporting the hypothesis that an ancient transformed structure has reactivated. The consequences of this awakening are not only scientific, but tectonic. Every major rupture adjusts the internal balance of the Antarctic plate, redistributing stress that may influence other regions hundreds of kilometres away. To the east, the South Sandwich subduction zone continues to thrust downward, while to the west, the Pacific-Antarctic ridge spreads slowly outward. Between these dynamic margins, the Drake Passage acts as a release valve, a place where horizontal movement relieves pressure from larger, deeper forces. But each release also creates new stress concentrations. It is conceivable that another segment could rupture in the months or years ahead, continuing a chain reaction that further defines the hidden boundaries of this oceanic domain. For Earth scientists, these events are a revelation. They demonstrate that even stable oceanic plates are not immune to sudden, massive deformation. Beneath the apparent calm of the polar seas lies a living planet, restless and perpetually adjusting its internal architecture. The Drake Passage quakes serve as a reminder that our planet's mechanical behaviour cannot be fully captured by the tidy lines of tectonic maps. Faults, once thought extinct, can revive. Zones assumed passive can rupture with unexpected force. The crust, it seems, remembers every scar it has ever borne. In the months following the quake, research vessels will likely traverse the area, deploying instruments to map the seafloor in unprecedented detail. Using multi-beam sonar and magnetometer surveys, they will search for linear ridges or offsets that betray the path of the rupture. Sediment cores may reveal layers of disturbed material, evidence of seafloor shaking or localized slumping. Each clue will add to the growing puzzle of how, when, and why this portion of the Antarctic plate failed. The answers could transform our understanding of polar tectonics, revealing how stress migrates across the globe in ways that are far from uniform. For now, what is known is this: the Earth has shifted again. The tremor beneath the Drake Passage was not an isolated incident, but part of a broader dialogue between plates, one conducted in slow, grinding silence over geological time. The tremors of 2025 are the latest sentences in that dialogue, written not in words but in fractures, ridges and waves of energy that travel through the bones of the planet itself. And as the sensors continue to record the aftershocks echoing beneath the cold Southern Ocean, scientists around the world are listening closely. For every pulse of seismic energy that passes through the crust carries with it the story of how our world breathes, moves and evolves. Somewhere in those vibrations lies the next revelation, a sign that the hidden fault beneath the Drake Passage has only just begun to tell its story. So, if you've made it this far into the depths of the Earth's mysteries, don't forget to like, share and subscribe, and tap that hype icon to help this story reach a wider audience of curious minds. The planet is always talking. It's up to us to keep listening.